if you're watching this, you already understand how to do part A, and you already understand how to find AE is 9 in part B. I want to go over a few other ideas that we can kind of get from this example though. So kind of an alternate way to find out that AE is 9 would be to acknowledge that if this is 21 and this is 14, if I do 21 minus 14, that would leave me with 7 for BD. Now, what you might notice is if BD is 7 and DC is 14, DC is just twice as much as BD. To get from 7 to 14, I just multiply by 2. And maybe you're thinking, well, if I just go from this part to this part by multiplying by 2, maybe that'll hold for the bottom part of the triangle as well. And indeed it would. I want to go over why that is though. So let's first think about 14 compared to 21. 21 was part of this bigger triangle, ABC. 14 is part of the smaller triangle, EDC. So I want to think about this smaller triangle being like a dilation of the bigger triangle. So what turns 21 into 14? What scale factor would dilate 21 down to 14? Hopefully we can see that that would be 2/3 scale factor. If I take this 21, I multiply it by 2/3, I get 14. If I take this 27, multiply it by 2/3, I'll get this 18. So these smaller sides are 2/3 of their corresponding bigger sides in the other triangle. What that also means, if this is 2/3 of the whole thing, that leaves this to be 1/3 of the whole thing. Same thing with this part. So these are both 1/3 of a whole side. These are both 2/3 of a whole side. So then hopefully it makes sense that if these are both 1/3 and 2/3 respectively, that these are actually proportional to each other in the same way. So if I wanted to solve for AE at this point, what I could actually do is create a ratio that said 7 is to 14. I compare 7 to 14. And that should be the same as if I call AE, let's call that X maybe, X to 18. Okay? So I want to put some words to these numbers over here. I got a 7, 14, X, and 18. When I look at 7, the words I say to myself are, 7 is this part of the big side on this triangle. It's a part of a side. Notice, this is not a side of any triangle up here on this diagram. It's a part of a side. And I'm comparing that part to the other part. I'm going one part to another part. I might even say smaller part to bigger part on this side. Smaller part to bigger part. Then when I go over here, smaller part to bigger part. X to 18. So I'm being consistent once again, even though it's a different ratio that I set up originally, I'm still being consistent in the way that I'm creating my proportion. At this point, we could do the whole cross multiply thing, and you would get X equals 9, just like we got in the other problem originally. I want to take this a step further though, and imagine a situation where maybe the problem said, hey, AB is 16, and I want you to find DE. That's X over here for DE. That's the unknown maybe that we wanted to find. I worry that if I didn't kind of go over this kind of thing, that a student might accidentally say, okay, 16, I'm going to compare that to X, I'm going to make a ratio, 16 to X, and this is a mistake, by the way. 16 to X is 7 to 14, right? Because it kind of feels good. I'm going left to right, left to right. Once again, once you've got a proportion, use words to describe the different parts of your proportion. 16, for example, is a small side of the biggest triangle, right? It's actually a full side within one of my triangles. And I'm comparing it to X, which is also a small side, but just in the smaller triangle. So these are both actual sides of triangles. 7, as I stated before, is not actually a side of any triangle. So this side of my proportion, I'm actually talking about sides of triangles. In my other side of my proportion, I should also be talking about sides of triangles. 7 does not represent a length of a side of a triangle. So it doesn't make sense to use that. So instead what I might do, if I go 16 to X, a valid comparison would be that 16 to X is kind of like 21 to 14. Because once again, if I use words to describe this 21 and 14, 21 is a side in the bigger triangle, and I'm comparing it to its corresponding side in the smaller triangle. So I'm going bigger triangle to smaller triangle, sides that correspond. Should be the same as bigger triangle to smaller triangle with sides that correspond. So once again, I have a valid ratio here.